All right, so now that we've laid the groundwork, let's just go ahead and take a look at each specific case. So in the first one, again, to go over an exponential growth model is basically given by the function f of t, right, equals sum a e to the kt. And since it's growth, this means that the k value that we're multiplying to the t is positive, right? A is usually the initial amount that I start with. So you can think of that as a y-intercept, if you would, if we were looking at a graph, right? And then k is a constant that usually needs to be determined. As I mentioned, it's usually a percentage rate, if you would, is one way that we can interpret that. But usually what we need is another data point, at some time value. I do know, the function value, and then we can use that to find my k, just like we have done on several examples when we were trying to find like the lead coefficient, I think one classic example is we had a x minus 8 squared plus k. Right, to find that a, we gave ourselves some data point and plugged it in. So the same thing's going to happen here. So the good news, one of them's easy. That a is always the initial amount, what I'm starting with, y-intercept. If there's another data points given, that's going to give me enough information to find k, as you will see. But right now, right, for the example that I'm giving you, right, I'm going to be nice enough and I'm giving you the model, right? So the amount of money in dollars in a bank account can be modeled by the function a of t, so its amount, equals 25,000 e to the 0.12 t, right? And t equals 0 corresponds to the year 2010. So in this case, I gave you the model. All we need to do is basically use that model. All right, and so so our first move then is to just start answering some questions based off of what we know. And the first question asks, is this a growth or decay model? Well, obviously it's growth, because I said it's growth, but for the big reason is our k value is 0.012, which is positive, right? So we basically have a nice positive number up in that exponent. We're talking about growth. What is the initial amount of money in the account 2010? So again, 2010 corresponds to the year t equals 0. So if we were to graph this function, right, what I'm telling you is that the y-intercept is at 0, 2500. If you're not convinced, go ahead and evaluate it, right? What is a of 0? Well, that's 2500 e to the 0.012 times 0. This is 2500 equals e to the 0, right? Because anything times 0 is 0. And then as we've learned, anything to the 0 power is 1. And so we get 2500, all right? So the initial amount of money that I have in my bank account when I started this investment in the year 2010 was $2,500, right? Next question, what is the amount in the bank account now in 2020? So again, in this case, t is equal to 10 because t equals 0 corresponds to the year 2010. So we've gone 10 years past that point. So as far as the model is concerned, we're looking for a of 10. So plugging that in, I get 2500 e to the 0.012 times 10. And for this model, I know if I multiply anything by 10, it just moves the decimal over. So I'm talking about e to the 0.12 value. All right, and so what's this equal to? Well, this time we need a calculator. So I'm just going to type it in the way it looks, right? Hopefully the glares are okay, right? So we got 25, we got 2500. Your e function, right, is the secondary function of the natural log key. So second natural log, and then what I have up there right now is 0.12, right, because I've already multiplied it by 10. And so what I'm getting is 2818. And how about it's like 74 cents. So 2818, if we round off to the nearest cent, and 74 cents. All right, so for this particular situation, if I started with $25,000 at about a 1.2% interest, right, that's what that K represents, then if I leave it alone, in 10 years, I'm going to roughly have $2,818.74. Okay, so that's basically what's happening there. When will my bank account reach 6,000? At this time, I'm not giving you the input, I'm actually giving you the output. I'm telling you that the function value is 6,000. So what I basically have to do is figure out when does my function equal 6,000. All right, and so now what we're basically doing, as we've done before, is finding out, solving for t. And since t's up in an exponent, we know we're eventually going to be applying a natural log at some point. But before we do that, first move is probably divide both sides by 2,500. I know a couple of zeros cancel out. 5 goes in there 5 times, and 5 goes into 60 12 times. So we have e to the 0.012t equals 12/5. I believe I canceled out right, yes, okay? And then to get to that t, I'm going to apply the natural log to both sides. Here, because I applied the inverse, we get 0.012t, and on this side we have 12 divided by 5. So divide by 0.12 to both sides, and what we have is t is the natural log of 12 over 5 all over 0.12. Of course, this is an exact value, right? So this is exact, but you know, we do have the calculator. Sorry, that's a 12 right there, you guys. So reaching over to my calculator, right, to find out what that time value is, what I'm going to do is take the natural log of 12 divided by 5. Make sure you close those parentheses, and then I'm going to divide that number by 0.012. And what we get is a value. T is roughly 72.9557. And so rounding off, this is really close to 73. So from 2010, add 73, we're talking about 2083. So under this model, again, if I left the money alone, which by that time it's highly unlikely, all right, but just that's what the model's saying, in 73 years, or in 2083, is when this $2,500 investment at 1.2% interest, right, will earn $6,000. Okay, so that is what we have for that. All right, and then another bend on this question is how long will it take the amount of money to triple? So that means we're taking the amount and it's basically being multiplied by 3. Well, remember the original amount was 2,500, right? That's what we started off with. So if I tripled that, right, we're talking about $7,500. So we're basically trying to figure out, when does my money equal, right? At what time does my money grow to $7,500? Because that's basically when it triples, right? Based off of my base amount. So again, we're basically solving the equation. 2,500 e to the 0.012t equals 7,500. Again, to solve for that t, I begin by dividing everybody by that, and when everything cancels out, we're left with 3, right? Because we're tripling. So e to the 0.012t. Again, applying a natural log to both sides, everything cancels out. We have 0.012t equals the natural log of 3. Divide by that decimal, and there's our exact answer. So t is the natural log of 3 divided by 0.12. All right, so there's the exact answer. However, I like this to make a little bit of sense, so we'll go to our calculator. So plug in the natural log of 3, and then we're going to divide that by 0.012. Oops, divide, I forgot my division bar. And what we get is 91.55. So 91.55, which is roughly 92. Now again, though, this is from 2010. So add 2010 to that. We're talking about, it looks like the year 3002. All right, so it's going to be a long time for the money to triple given this mathematical model. All right, so before you start saying this is ridiculous and all that other stuff, because it does. This is how money grows. All right. However, what ends up also happening in the bank account is that not only does your money just sit there, growing in principal, but you are actually contributing to your bank account. So if you do that on a nice consistent basis, your principal, that rate is growing for you 2 ways. One, just by earning interest like we're doing here, but also by you investing some money in there. We actually call that an annuity. I'm getting a little bit more off, getting deeper into this, but it's really surprising to see how much money you can earn, right? Even with a relatively small percentage rate, if you let the money grow for you, and then you also keep packing a monthly payment to yourself every month. However, we're kind of pressed for time. I think those examples would have been in 6.7, but I went ahead and skipped them because the formulas are very complicated for the time of year that we're at. But you can hopefully, just after seeing how our money grows, just by sitting there by itself, you can imagine if I keep adding to the principal with a little bit of a payment to myself, it grows even more. All right, but there's your exponential growth model. Again, population dynamics, spreads of viruses, bacteria growth, all that kind of stuff behaves in a very similar manner. All right, but there's growth. Let's go take a look at example of decay.